I will be discussing one of the inner parts of the driverless AI product, which is called the data table. Okay. So driverless AI, which is a main product of H2O right now, is in essence consists of two parts. It does automatic feature engineering and then does automatic model fitting to those features that it builds. And it does so iteratively through many hours of hard labor. But in the end, these are two main parts. And at the very beginning, when we set off to make this product, we understood that feature engineering is going to be a big part of this journey. So what did we going to do with it? The first obvious choice is Pandas for feature engineering. Everyone is doing that. But then also everybody who is doing it saying that once you have a really big data, it becomes really slow. And it has several other unfortunate characteristics, such as being very memory hungry. So in early it can easily blow up 200 gigabytes of RAM when you are, say, a 2 gigabyte data set. So this was something that was not acceptable for us. So next choice. Next choice was a GPU data frame, which is very good because it's very fast, unlike Pandas, but it's not well suited for big data either, because it's the size of data that it can handle is limited by the amount of GPU memory. And it also, the problem that it has is that it consumes the GPU resources. And for many people, this is not a problem. This is actually a feature. For us, we consider this a problem because we have these two parts, the feature engineering and the model fitting. And the model fitting we already do inside GPUs. So if we were also to do feature engineering inside GPUs, then it would mean that everything we do in the GPU and the CPUs on the machine are just being idle, and it's a wasted resource. So we decided from early on that what we want is to have the split between GPU and CPU, that GPU will be used for fitting the models, and CPU will be used for model engineering. So we decided that, that it's time for us to make our own product, and it's called the Datatable. And it is built upon a blueprint of ours data.table, which if you probably know what it's suitable for big data. And yeah, all right, that's better. So we wanted to do multi-threaded data processing. So because on a big server, you usually have many cores. So and traditional solutions such as Pandas are single-threaded, and even our data.table is single-threaded in some operations. So we wanted to be all in multi-threaded support. We wanted to be able to support really big data. And when we say really big data, we mean something that might fit on a hard drive, but doesn't necessarily fit on in memory. That's because we might be dealing with problems that are way too big even for a single machine to fit in memory. Even on a server with 200 gigabytes of data, you might want to have a data set, let's say, of 100 gigabytes, and then holding it all in memory would be very problematic. So we wanted to have a solution that would support that kind of use case. We wanted to have a solution that was really conservative in how it uses memory, because that was one of the biggest problems of Pandas that we were seeing, that once you start doing anything with Pandas, it tends to blow up through your memory really fast, especially if you're trying doing multi-threaded, multi-processing something, and it creates just multiple copies of everything in memory. So we also wanted to achieve really high speed by using efficient algorithms from our data.table, and we also wanted it to be open source. So this is a separate, it's a product that is used in Driverless AI, but it is also a separate package that anybody can use for their own data science needs. Next. So current data table features that we already have implemented are the following. So we started from being able to ingest data, and that's one of the really slow parts in Pandas, for example. So first thing that we did was parallel reading and writing of CSVs, because everybody in data science uses CSV as a main data format for storage and transfer of data between the different products. The next thing was to convert from Pandas, NumPy, and back. And we did this because we understood that this product like this doesn't happen overnight. So there will be some features that are lacking for a very long time. So in order to circumvent that deficiency, we would need to be able to fall back to Pandas or to NumPy whenever we don't have some feature implemented. So the transfer between Pandas and NumPy should be really fast and built in from the very beginning. We also wanted to build to saving and opening into binary format, and that's a place where Datatable really shines because first of all, it saves into binary format really, really fast. And then it opens that binary format in no time at all. And no time at all meaning like milliseconds, as opposed to, say, feather format that takes several seconds to open a file that you were previously saved. And this is, again, very useful feature for Driverless AI because we're saving things in one process and we open them in all other processes. And it takes no time in any of these processes to open those files, and it takes no memory, additional memory, to actually use those files. So then, of course, the main features of a data frame are columnar expressions, selecting data, updating, deleting, sorting, joining, grouping. Sorry, joining is minus because it's not implemented yet. And then some of the other features are still not implemented, still on our roadmap, and we are working hard to make them implemented. Next, please. So, in order to demonstrate in numbers what are we talking about potential speedups, we first start with reading CSV files. So Datatable uses function fread from our data.table developed by Matt Dowley to read the files. And as you can see here, this is a sample of few files ranging from 600 megabytes to a couple gigabytes. The blue chart is the time how long it takes to read a file in Datatable, and then red in Pandas or brown. And the first data set, Pandas crashed, so there is no time there. But for all others, you can see that speed up is several times over. And the green bar, by the way, is called Pandas via Datatable. It means that we first read in Datatable, and then we convert to Pandas. The conversion to Pandas involves some overhead in some cases, but you can see that in all of those cases, it turned out to be actually faster than using native Pandas reader. So it means that even if you don't want to learn anything about Datatable, you can still have the benefit of having a fast CSV reader by just doing a read in Datatable and then immediately convert to Pandas, and then you have your familiar Pandas data frame. In our tests, Datatable can actually handle much larger data sets than a couple of gigabytes. We were able to successfully load a 60 gigabyte data set on the very laptop that is back in that back room, back corner there, which has only 16 gigabytes of memory. So something that would take hours on Pandas before it crashes the computer and without finishing the job. So this ability to really work hard to ingest unlimited amounts of data is something that, that we wanted to achieve. Next, please. So the next step is writing CSVs, because once you did any kind of transformation, you want to also be able to to some other application, maybe to Spark, maybe to NumPy, maybe to R, whatever your framework of choice. The most portable solution is to actually, again, a CSV. And in Datatable, we write it so fast that you can barely see that blue bar on the left. So the speed ups are like 70, 80 times compared to Pandas. And for comparison, we also show the green bar, which is feather format. So it's not really fair for comparison. As you know, feather is a binary format. Binary is much easier to write than CSV. But you can see that in some cases, the green chart is actually higher than the blue chart, which means that it takes longer to write a binary file than to write a CSV file with data table. And that happens only when you have a string data in your data sets, which is basically always, well, not always, but most of the time. So you can see that on the right-hand side, the ratio of how long, the ratio of data table versus Pandas speed up. So 20, 30, 60 times for some of the data sets. Next, please. As I said, it's not exactly fair to compare writing binary in feather versus writing binary versus writing CSV in data table. So why don't we compare writing binary versus writing binary? And this is exactly such a comparison. So again, we can see that in almost all cases, except for the very last one, I don't know what happened there, but usually a data table is much faster than Pandas, at least several times, but not too fast, because writing binary is comparatively easy, and data table good feather format does a comparatively good job in that. Next, please. So, and this is a reading binary, something that I mentioned before. So again, blue is data table, and you don't see it here because it's all 0 pixels. The amount of, it takes several milliseconds each time. So when you divide 5 seconds by several milliseconds, you get thousands of times faster. So it's really instant, and this is what we like about it, because the ability to have your data set on disk and then to say open, and suddenly it appears, and no time is spent, is something that just very convenient for you. Even though, of course, you understand that the data is not loaded into memory, it's mapped lazily. This is a feature of memory mapping, but it's still advantageous for you, because in almost all kinds of analysis that you do, you will never be using the entirety of your data set. Usually you would use some of the columns, for example, and some of the other columns you might not need for this particular task that you have in mind, which means that loading the entire data set into memory is going to be wasteful. And if you avoid loading that, if you do it lazily through memory mapping, then you don't waste that time. Next, please. So now we go to real data frame features. Sorting. Again, this is an example of sorting integers in a range up to 1 million. And we look in the chart. It's a log plot of how much time depends on the number of items in your array. And you see that the difference is approximately an order of magnitude, and actually grows with n. And that's because Pandas uses a conventional comparison sort algorithm, and Datatable uses a radix sort, which is a O of n algorithm. So it grows slow. The time grows as O of n, and this is why the speed is actually the speed up becomes bigger the more data you have. And on this left-hand side, you can see that the speed up, even at the smaller range, is around 4 or 5, and at bigger n, it becomes around 10 or 20. And at
at around a billion data points, the data table took around 70 seconds to finish sorting, and Pandas didn't finish sorting. At least I grew too impatient to wait for it to finish sorting. So it's possible that whatever algorithm that you use, they just become so much resource hungry that Pandas cannot finish. Next, please. Grouping is another big thing, and it also one of the crucial thing for that underlies many of the feature transformations that we actually do in the driverless, and we also get some amount of speed up compared to Pandas. Not as much as in previous examples, because if you ever looked at the documentation for Pandas, they say that they use very efficient and very fast algorithms, so presumably it's fast enough. So in some cases you can see that a speed up difference is almost 1, but in other cases it's more than 1. It's 3, 4, 5. So the charts here, let me explain a little bit. So grouping is a problem that is two-dimensional, because it depends on the number of elements that you want to sort, and then the number of groups within those elements. So if you have few groups, it's a different kind of problem than if you have as many groups as the number of rows, for example. So K in the right-hand chart is actually the approximate number of groups within the array. So the lighter tones correspond to more groups, and as you can see, at least on the very right side of the chart, that for really large ends, you have bigger speed ups for bigger number of groups. So if you have a large number of groups, the speed up of the data table will be more significant than the speed up of than the speed of Pandas. So yes, I think that's basically all that I wanted to show you. The idea that we wanted to build a product that uses a more efficient algorithm and uses out of memory mapped data storage to achieve high efficiency and high throughput, at the same time as using very low amount of memory overhead compared to traditional solutions such as Pandas. And that solution underpins the technology that lies within the driverless AI and allows it to achieve the great results that you saw in other presentations. So, thank you.
You gotta turn this on. It's on. Off. Oh.
So it's okay. I'll just yell again. We have 2 questions. One is Datatable restricted to the capacity of a single machine? How about distributed computing?
Yes. So the answer to that is yes. It is restricted to a single machine, and that is specifically because we have another product called H2O, and it was 5 or 4 years in the making, that was specifically built for distributed computing. And we understood that once you build something for distributed computing, it involves certain overheads that are just not, they're just too much when you try to employ them in a single machine. So since we wanted this for driverless AI, which was built for single server machines, this was built from the very beginning as a single machine solution, and there is no support for a network of machines.
Thank you. We have one more question. Will Go AI ultimately adopt the data table as well? And for those of you that don't know, Go AI is the GPU Open Analytics Initiative, which H2O is a part of.
So Go AI currently they sponsor PyGDF, the GPU-based data frame, but I don't see why they wouldn't be opposed supporting multiple data frames, because each of them is a niche for its own needs. So data frame in GPU and data frame in CPU are both solutions that are needed for specific tasks. So why not?
Thanks so much, Pasha, and thanks so much, everyone,